Lab, you're going to do an MCO455. What you should fill in is your first name, last name, or family name. Should fill in your student ID number here, and then you should select which lab section you're in. So what you have to do is circle A or B or C, whatever your lab section is. Now if you don't do that, there's going to be one mark taken off, because that means that the instructor marking this is going to have to search through their records to figure out which one of these piles of A, B, C, D, and so on that you're in. And if it takes them more time, you should lose a mark or so, because that's really making their life difficult, and you really want to make your boss's life easier in real life. Now the first thing we're going to do is we're going to start with a binary program. Now binary programs are what we used to use back in the 60s, because our binary programs were written for a computer system back then that basically was just nothing more than switches and LEDs. So there's our program instruction here, and what you do is you put in your starting address for your program, which would be typically in RAM, and then you would say, okay, here is a 1, so I'd flip this switch up. This is a 0, so I'd flip this switch down as it is now. This is a 1, so I'd flip this switch up, and so on. So you'd be entering your program with a series of 8 switches. You'd come over here and hit the deposit, and it would put that instruction in memory. Then you would enter the next instruction here, and so on. And that's how you used to program back in the 60s. And when your program was entered, you flip from halt to run, and your program would indeed run. And that's why we have this binary program, because right at the machine level, and that's what these old program computers used to do. This was programming right at the level of the machine of TTL voltages, highs and lows, and it understood that directly. So if we go back here, what we want to do is convert this binary program into octal. And you're saying, why octal? Well, in the 70s what they did was they started grouping switches in groups of 3, and 2 to the 3 is 8, so that's why it's octal. So what you're able to do is write a program in a little bit more compressed form in base 8 and be able to spot if, was this a 6 or was this a 5? You can't really easily see here, but it's very easy to see in octal. Once we've got that conversion from binary to octal, the next thing we're going to do is then convert from binary to hex. Now hex is base 16. And 2 to the 4 is 16. And why are we doing that? Because if we take a look here in the 1980s, you would press an A and it would generate the pattern for an A, which is a 1010. You'd hit a 5 and that would be a 0101. And this is the kind of programming that we did back in the 80s. So what we're going to do, and you're looking here and you're saying, well, what does this program do? Well, this program, looking at it, because I happen to know, actually loads the number AC, adds a number 3D, and stores the answer in an address, and continually sits in an endless loop. So even though we're converting binary to octal and binary to hex, these are really program instructions. Now you should be able to do this without a calculator, and that's what this exercise is all about. So let's take a look and see how we go about that. First of all, if we're going to be converting from binary to octal, octal, as I said, is base 8. 2 to the 3rd power is 8. So that's why we group all of our numbers in groups of 3 and put weighting factors of 1, 2, and 4. And if you think about it, all of these numbers of weighting factors 4, 2, and 1 will generate any number from 0 to 7, which is really what you have in base 8. So if we take a look at grouping these in groups of 3s, 3, 3, and we only have 2 here, because we have 8-bit numbers are the size of an 8-bit microcontroller or char data type also in C. And the way you do the conversion is quite simple. If this has a 1 underneath a weighting factor, then you add that weighting factor, and since this digit is here, we're just going to put a 2 in there because we have a 2 but no 1, so that adds up to 2. Here, if we look at these 3 weighting factors, this is the only one that has a 1 under it, so we put a 4 here. This one here has 2 1s. It has a 1 here and a 1 here, so 4 plus 2 is 6. And it's very easy, as you can see, to convert between binary and octal just by grouping in 3s. Let's pick a little bit more interesting one down here. This one here again is 2. There's our 2. And again, 4 and 2 is 6. There's our 6. And here we have 4 plus 2 plus 1 is 7. So it's very easy to convert from binary to octal without really worrying too much. So once we've got this filled in, and we should draw lines across here to make sure things line up, the next thing to do is go binary to hex. Now hexadecimal is base 16, and what we're going to find is that base 16 or hex, decimal goes 0 to 9, hex goes 0 to 9. But once you get past 9, in decimal the digits repeat. You go 0 to 9, 10 to 19, 20 to 29, and so on. But in hex there's 16 single digits. So when we have 10 in decimal, that becomes an A. 11 is a B, and so on down to 15 is an F. So we're going to need to know that to be able to convert to hexadecimal. Now what we do is we break our things in groups of 4. Why groups of 4? Because hexadecimal is base 16, 2 to the 4th power is 16, and therefore we group in 4s. Now if you take a look at our weighting factors, I think you can understand that you should be able to generate any number from 0 to 15. So if we have all zeros, this would be 0. If we had all ones, here we go, all ones here, this would be 8 and 4 is 12, 13, 14, 15, and 15 when you look it up in your chart is an F. So it's really that simple, is to again add the weighting factors and go to this column here. Now if we look back at what we have to do for the next part, is we're given an octal program, and what we have to do is convert it to the other two. Now the simplest thing to do is actually write in weighting factors 1, 2, 4, 1, 2, 4, and 1, 2, and then work it back the other way. So if we take a look here, this is exactly, if we want to work this backwards, if we were given 2, 4, 6 and we want to go this way, if we have all our weighting factors written out here, 1, 2, 4, 1, 2, 4, 1, 2, then the only way we can make a 6 here is a 4 and a 2. So it's very easy to convert back, and the same can be said for doing the hex. So the things you should be able to do is go octal to binary, binary to hex. And for this particular exercise, it's simple to go hex to binary and then regroup in 3s to go from binary to octal, and you should be able to fill this in fairly quickly. Now let's take what we've learned from hex, binary, and octal conversions and take a look at all the different possible 8-bit conversions we can do. Later we're going to look at this and say that 8-bit number systems for C are char, as we should know from before. So what you should be able to do right now, because this is a question that will show up on your term test, and this whole question, a half mark per conversion, gives you a mark out of 10 on your term test and your final exam. So you should be able to go from hex to binary, and then binary to octal, or in this case you should be able to go to binary to octal, binary to hex. And one thing to be careful with, if you look here, there's 4 bits there and it says 8 bits, there's only 3 bits here. And what that means is that what you have is you have to add a leading 0 here. And so you should be able to fill in hex to binary to octal. So you should still be able to do these conversions in here and fill in 6 here. But the next step is you say, okay, well, what is this BCD? BCD, if you look it up, stands for binary coded decimal. What does that mean? Well, if we look here, that means that every decimal digit from 0 to 9 is coded up as a 4-bit binary number. Notice it's sort of like decimal to hex, except there's no A, B, C, D, E, or F patterns. There's just 0 to 9. So what we can do here is let's convert BCD. I'll give you one here. This is 1, so the first digit over here is a 1. This is, if we look at this, this is a 1001, and if you remember from before, a 1001 is a 9. So what this is it's a 1, 9, and if you look this up, it's 8. So we write down 198. Now the same thing over here, if you got a 221, what you can do is write down the 221 and figure out the factors that we've got here. So this would be 0, 010, 0010, 001. So you can see that there's a relationship between binary octal hex by just grouping, binary to hex in groups of 4, binary to octal in groups of 3, and decimal to BCD in groups of 4. So that's pretty much all you have to do part of this chart. The only thing that you have to do is figure out, well, if I've got a relationship between these 3 and the outer 2, how do I get a relationship between these 2 here? And so the simple thing is, if we want to go from decimal, which is say 221, to hex, we'll see that there is a procedure for doing that. And let's take a look at that next. Convert between decimal and hex. You simply divide 16 into this number. Whatever the quotient is will be the first digit. Whatever the remainder is will be the second digit. So let's take a look at an example that's in the book. And this one is on, let's take a look, this one is on page 8. It shows you how to convert decimal to hex. So 16 goes into 21 once, and 16 times 1 is 16, so there's our 16. We subtract that and we're going to end up with 5. We bring down the 2 to make it 52. Divide 16 into 52 goes 3 times, and 3 that is 48, and when we're finished we subtract this and we get 4. So the remainder here is 4, so that's going to be our rightmost digit, but our quotient, which is the most significant digit, is 13. 10, 11, 12, 13, A, B, C, D. So our answer is D4, and it's really that quick. So let's go back and take a look, because the number we have is not the number that's in the lab. The number in the lab is 221. Now if you do it, and I'll walk you through this as you're writing it down. If you write it down, 16 goes into 22 once, 16, 6 remainder. 61, 16 goes into 16, sorry, 61, 3 times with 13 remainder. So you're going to have 13 as a quotient, which is D, and a remainder of 13, which is another D. So you have DD, and then you can convert this here. Now to go back the other way, let's take a look at this, and it shows you on that same page that we just referenced, but if you look here, in decimal, this is 10 to the zeros place, which is the ones place. This is a 10 to the 1, or the tens place. This is the 100s place, which is 10 to the 2. So 10 to the 0, 10 to the 1, 10 to the 2. 2 100s, 2 10s, 1 1. And you add those together and you get 221. Now in hex, it's this way. You have, this is the 16 to the zeros place, or the ones place. So we have 6 ones. And over here, what we have is 10 16s, or 16 to the 1. So 10 16s plus 6, 160 plus 6. So the answer here is 166. Now, when you do the conversion back, just to check 16 into A6, remember what you have to do. You have to always divide twice. So we divided twice here, because if you divide 166 here this way, what you're going to end up with is, when you go back here, you're going to have a 1 6. Now if you divide twice, 16 goes into 6 0 times. 6 minus 0 is 6, and that will give you the right answer, 1 0 on top, which is A, and 6. So you always have to divide twice. Once you've done that, you should be able to fill this entire chart in. And don't forget, what we're talking about, 8-bit unsigned conversions, are really in C, 8-bit unsigned char. At this point of the lab, we have completed question 1 and question 5. So let's fill in what we missed in the middle. So question 2A says, using an Ascii chart, which stands for American Standard Code for Information Interchange. So this is just a North American code. Canada and the US, does not work in other parts of the world, such as the Middle East or China or whatever. So this is specific to North America. And so what you're going to need for that is an Ascii chart. Now in the notes, in the introductory chapter on page 9, there is an Ascii chart. Now I would never ask you to do something like this without an Ascii chart. So let's see what we have to do. As it says under here, we have to write the hex digits underneath here for our message, but to do this we have to write the actual ASCII characters under here for the actual message. So this is hex to text, this is text to hex, and that's what we really have to do. So let's take a look at the first digits is 59. So let's take a look at what 59 is. Now notice we've got decimal, hex, and char. So we're going to look at the hex. So 59 in hex, if we look down here, is a capital letter Y. So that's our first letter. So as we go through this, what you're going to find is you're going to write a capital letter Y here. When you look this up, a small letter O, this is a small letter U. And when you look up to 20, a 20 is a space. So you just put a dash here to indicate that there's a space. So it's capital Y, small O, small U, dash, and then whatever the rest of the message is here. Now to go the other way, you're going to look up a capital letter A here, and when you get the capital letter A, you're going to write down the 2-digit hex for the A, the 2-digit hex number for the small letter R, 2-digit hex number for the small letter E, and here underneath this space, and there's one space here, one space here, one space here, put a 20, because 20 is a space. So once you get that filled in, we're able to then do the next thing, which is adding and subtracting in hex. Answer question 3, we're first going to look at how to do adding and subtracting in hex. And we have these NZVC things here that we're going to look at later. We're also going to then, once we do the adding and subtracting in hex, we're going to look at adding and subtracting in binary. And we will eventually get back to this. So the first thing is the adding and subtracting in hex. We're going to look at the answers, and then this is going to give us a context in which to understand are the answers valid in different number systems, and we'll also be taking a look at number systems to make that happen. Now if you take a look at question 5 here, question 5 is 8-bit unsigned conversions. However, if you look at question 6, this is 8-bit signed conversions, so we're going to be looking at the difference between signed char, unsigned char, signed and unsigned integer as well. So let's get started on taking a look at the adding and subtracting in hex and in binary.
Okay, what I want to demonstrate to you right now is how to add numbers in hex. And we have this AB plus CD. What we want to remember is a decimal and hex have this relationship 0 to 9, 0 to 9. But 10 is A, 11 is B, and so on down to 15 is F. So how we would normally add is we would start with 2 digits like this. And we know how to add in decimal. So if we look at B, B is 11. D, when we look at it here, is 13. So we can add those two numbers and get 24. Now what we have to do is since it's in decimal, is convert this back to hex. And the way we do that is we can divide 16 into 24. 16 goes into 24 once, 16, 8, and so our number here is equivalent of 1, 8, this is base 10, 1, 8, base 16. And you're saying to yourself, okay, what do I do? Well, the 8 here goes here, and the 1 carries to the next column. So this is 1, 8, base 16. So all we have to do to finish this is to add these three numbers here. So that's 1 plus 10 plus 12, which is 23. And when you work it out, that becomes 16 plus 7. Now our answer is 78. It's an 8-bit number plus another digit called a carry. And that's how you basically do hex addition. Now one of the things that you'll see is that hex addition is a little bit tedious, but hex subtraction is easy, comparatively speaking. So here's the way it works. If you have this digit, which is D, is bigger than B, you have to borrow. And where you borrow from is this guy. So you borrow 1 from the A is 10, 1 less than 10 is 9. And what we do is we slide a 1 over here, and this becomes a 1B base 16. Well, 1B base 16, that's 16 plus 11 is 27. 16 plus 11 is 27. And we're subtracting D, and if you remember D here is 13. So we subtract those two, we get 1, 4. We look that up, that's 14 is E. We've already done half of our subtraction. Now, we have another problem here because C is bigger than 9. Now, just like when you don't have enough money, you go to the bank. So what we do here is we take out a loan, we take out 1, we set the carry so we can borrow from it. So if you borrow $1,000, then you use $1,000. What you owe and what you use balance out. So these two cancel out, but what we have here now is this column is now not what it was before. It's 16 plus 9, or 19 base 16. 19 base 16 is 16 plus 9, and if you do the math, that's 25. 16 plus 9 is 25. Subtract C, which is 12, and that gives us 3 and 1, so that's 13, which when we look it up is D. And that is how you do subtraction. If this number is bigger, you borrow 1, reducing this by 1, and you slide 1 over is 1B, which is 16 plus 11 is 27. Subtract this, gives you 14. If this digit is bigger than here, you set the carry so you can borrow from it. That's why it's called either a carry when you're adding or a borrow when you subtract. It says you borrowed. Here you are borrowing 16 plus 9, 25, minus 12, 13. There's your answer. Now, this is a fairly easy subtraction. Let's look at the most complicated subtraction I can ask you to do. Let's take a look at this number. 0, 0, subtract AB. And this is what I call the hardworking Bob and lazy Joe scenario. And Bob has always said that good, honest, hardworking people get done in by lazy people. So here's Joe, and Joe says, well, I need to borrow. But Bob here says I got no money. So Joe tells to Bob, go to the bank. So Bob takes out a loan, and now Bob has $16. Here's his borrow, he now has 16. Now lazy Joe over here says, oh, you got $16, let me borrow from you. So 16 for Bob now becomes 15, and Joe, the lazy guy, has all the money, he's got 16. So this becomes 16 minus 11 is 5, 15 minus 10 is 5, and there is your toughest subtraction you can possibly ask to do. Let's take a look and see how we add directly in binary. And again, we're going to do it bit by bit or digit by digit, so here's the way it's going to work. We're going to add 1 plus 1. Now we have a number of options here that when we add two 1-bit numbers, we can have a result of 0 with no carry, which is a 0. We can have a result of 1 plus no carry, which is a 1. We can have a result of 0 plus a carry. We can have a result of 1 plus a carry. So in this case, 1 plus 1 is 2. 2 is 1, 0. So we write the 1 up here, and we write the 0 down there. 1, 0 is 2. Then we have 1 plus 1 is 2, which is 1, 0. 1 plus 1 is 2, which is 1, 0. 1 plus 1 is 2, which is 1, 0. 1 plus 1 is 2, which is 1, 0. Now we have 1 plus 1 plus 1, which is 3, which is 1, 1. We have 1 plus 1 is 2, which is 1, 0. And we have 1 plus 1, which is 2, which is again 1, 0, where this is our carry. And there is our 8-bit result. Now there's two ways to do this. This is the way you can do it in binary, and your DGS class should show you how to do this. But we can also do this same calculation in hex if we convert. Now, if we convert this, this is 8 and 2, which is A. This is 8, 4 is 12, plus 1 is 13, which is D, plus this number here is 73. So 13, 14, 15, 16, which is 1, 0. There is our 0 here. And then 7 and 1 is 8, that's 18, which is 1, 16 plus 2, and there's our 2. So we do indeed see that this binary calculation that we're given can be done in hex and converted back, or if you're quick, you can do it directly in binary as shown in DGS. Now, if I give you a question where I ask for a binary addition, I expect the answer in binary. If you can convert it to hex, do it quickly and convert back, that's good as well. Now, when you're subtracting in binary, the easiest way to do this is to actually convert the values in binary to hex, do the subtraction, and write it back. So let's see how we go about doing that. So this number is 4 and 2, that's 6, and 8 and 4 and 1 is 13, and this is again 13, and this number here is B. Now right away you can see that once you get good at doing these conversions, this number here is 13 minus 11, which is 2, so you got half of it done already. You have to borrow because the D is bigger than the 6, and then you use it. So these balance out. So 16 plus 6 is 22 minus 13. And once you got that, the answer is 9. And when you do this, then you can write the answer back as a carry. 1, 0, 0, 1, 0, 0, 1, 0. This is the fastest and most accurate way to do it. However, when you're taking DGS, they will show you the 2's complement arithmetic, which will get the same answer, but it's going to take a lot of steps. Let me show you what the DGS teacher is going to do. So our answer, let's just write it over here so we remember, this is a 1 in hex, 9, 2. So just to remind ourselves. So here's what it does, because digital circuitry cannot subtract directly. It uses a trick. So here's what the digital teacher will tell you, is you take this number and you put it through 8 inverters. Because digital circuitry has inverters. What does an inverter do? Well, all ones become zeros and zeros become ones. So this is 0, 0, 1, 0, 0, 1, 0, 0. This number you have here is called one's complement. Okay? And one's complement, if you add 1 to that, this becomes a 2's complement. 0, 0, 1, 0, 0, 1, 0, 1. And the 2's complement, as we'll see later, is the negative of this. Then what do they do? Well, then they say, okay, well, let's get rid of this guy and turn the subtraction into an addition. So let's get rid of our inverters here. Let's take this number back and we're going to add that back to here. So this becomes 0, 0, 1, 0, 0, 1, 0, 1. And if we do this again, 1 and 1 is 2, which is 1, 0, 0, 1, 2, 2, 0, 1, 2, 2, and 1. And notice our carry here is not right. So we've got 9, 2, just as we had before. But what the digital circuitry is smart to say is, even though we have a 0 carry, it's smart enough to realize that you were doing a subtraction, not an addition. So what it's going to do is it's going to run this through an inverter and actually give you a 1. So the intuitive result we came up with, which is 92 with a carry, is exactly what the digital circuitry will come up with, but I think you'll find that this way of doing it in hex is a lot quicker to get your binary subtraction.
Now, one of the things that we saw before is there's a relationship between hex binary and octal. There's a relationship between decimal and BCD. So the only real conversion that we have to really be aware of is really decimal to hex. And so hex binary and octal, these are just 3 different ways of saying the same thing. So the only real information that we want is in the most compressed form of binary, or hex. So let's take a look at relating the decimal to the hex. And what we can do is make up a number line and compare it. Now we're going to see that there's a certain relationship for 8-bit unsigned conversions, or 8-bit unsigned char. And when we look at question 6, we're going to see there's a slightly different relationship between decimal here and hex in terms of how the 8-bit signed char works. So let's take a look and see how that is different.
And one of the things you're going to see is in P or G, you did unsigned char and signed char. Now you may not have spent a lot of time doing signed char and unsigned char, but this is going to be very critical to what we're working on in MCO. Now the concept is here that if you have voltages from 0 volts to plus 10 volts, then it makes sense to use unsigned char. And one of the things that you'll see is, based on what we looked at, the decimal number here is given by the first digit times 16 plus 15 is 127. 16 goes into 127, 7 with 15 remainder. 8 times 16 is 128 plus 0. 15 times 16 plus 15 is 255. 16 goes into 255, 15 times and 15 remainder. So we have this relationship, which is nice for doing unsigned conversions. But what we're going to see is the most significant bit, which is referred to as our end bit, for this entire range from 0 to 7. If you look at 0 to 7 in binary, the most significant bit of all these digits is 0. In fact, 0 is 0 with 7 zeros, 7F is 0 with 7 ones. So all the numbers in this range have the most significant bit or end bit as 0. All of these numbers here have the most significant bit or end bit as 1. So 8, 0, which is a 1 followed by 7 zeros, all the way up to 1 followed by 7 ones. All of these numbers have the most significant bit 1. But when you're talking unsigned, all of these numbers are considered to be positive, and there is no negatives. So you go 0 to 255 decimal, which is on 256 numbers here, all having positive numbers. So one of the things you're going to see about unsigned char is the most significant bit, which is their end bit. Doesn't matter whether it's a 0, doesn't matter whether it's a 1, all of these decimal equivalents are all positive. Why do we have this? Because we have positive voltages. We want to have all positive numbers to represent these values. However, you're not always going to have all positive values like a single-sided supply. Sometimes you'll have minus 5 volts to plus 5 volts. And when you have that, you're going to need to have half your numbers negative and half positive, and that's why we have something called Sine Chart. And what you find here is if the MSB is 1, these numbers are considered negative. If the MSB or N is 0, they're considered positive. So in the case of Sine Chart, N, or the most significant bit, divides the numbers into 2 equal halves. Notice that we have here, these numbers here from 0 to 7F are the same as these sine numbers 0 to 7F. So 7 times 16 plus 15 is still 127. 16 goes into 127, 7, 15 remain, no problem. But what you run into is that how do we make FF showing up as negative 1? Because FF is 15 times 16 plus 15 from 2 to 55 and so forth. But this is a different FF. But one of the things that you should note is that these numbers here, from this range here, 80 to FF, has been slid over intact over this way here. And how far has it been slid? If you look at it, FF is 255, this FF is minus 1, so that's 2 to the 8 places that this is shifted over, which is 256. In fact, this entire section here that have MSB1 has been shifted 256 steps here. That's going to be important when we take a look at doing sine conversions. Now, sine conversions, all these numbers here from 0, 0 to 7F, same as before, but if, for instance, if we want to take a number here, like A6, and we want to find out what is A6 over here as a sine number, you can see that they're different. This A6 is different than this A6 by a shift of 256. How would you find out what this A6 is as a negative number? Well, first of all, what you do is you figure out what it is as an unsigned number. In this case, we're going to find that that's 166. And then you say, well, this A6 is definitely not 166. It's some number between minus 1 and minus 128. So how do we figure out what that is? Well, this number to this number is offset by 256. So you could say 166, subtract 256 and you have it. But since we have no calculator for this course, we can just write 256 minus 166 and flip the negative sign. So that's 0, that's 9. So our answer over here is minus 90. So that's how you can work it out. Any numbers that have MSB 1, you can just do the calculation as before, subtract it from 256, flip the sign, and that's your value. If you were given minus 90, how do you go the other way? Well, if you subtract 256, the simple thing here is to add 256. So we start with minus 90. Minus 90 plus 256 is like subtracting from 256. This is 6, and so this is going to be, we get into a borrow, so that's 9 and 6, and that's a 1. Now to put this back, this is 16 into 166, that's ones. Bring down to 6. Now, the thing is, what you have to do is divide twice. You can't just divide once and say that's 1/6. You have to divide twice. So 16 goes into 6 0 times with 0 remainder, and our answer here is A6, just as before. So this is how you can do signed conversions.
Now notice to get this one, we add 256, you convert that to hex like it was shown in the previous section, and you've got these three. DE, you do the conversion as before, 13 times 16 plus 14, and you subtract that from 256 and put the sign over here. Notice here, this tells you right now, with the most significant bit being 1, that the answer over here is going to be negative. In fact, when you work this out, DE starts with a 1, so that will be a negative. But when you do this one here, 124, that's a 0, 1, right? And the 0 means that that is in the positive range, and you do not subtract 256. So this one will be positive, and these three here will indeed be negative. So make sure you take that into account when you're filling in this chart.
Okay, if we look at our unsigned char line here, which is a relationship really between hexadecimal and decimal, what we find is if we do certain calculations, we're going to run into trouble. Because if we say FF plus 1, and the calculation isn't that difficult, it's 0, 0 plus a carry. But what does this really mean? It means I had $255, say, I get another dollar, and now I've got only $0. I got nothing. Because our variables are going to be char variables that these things are contained in, or answers, and this result of extra 9th bit here, or carry, will not fit into a char or 8-bit variable. So we've lost some of our data here, so FF plus 1, this carry here indicates something called an unsigned overflow, because our number is too big to fit into our 8 bits. Let's take a look at another calculation. Let's look at 0.3 subtract 0.5. So if we do the calculation, it's the lazy Joe and hardworking Bob scenario again. Joe needs money, Bob doesn't have any, so he sends him to the bank, he gets 1, he's now got 16, Joe hits him up for a loan. Poor old Bob has got 15, now he's got 16 plus 3, so that's 19 minus 5 is what, 14, which is E, FE. And so what does this mean? What this means is I went 3 units this way, and I turned around and I went 5 units this way, and I wrapped all the way around here to FE. What that means is I said 3 subtract 5 is 254. It doesn't make sense. So anytime you have a carry or a borrow, what this really means is an unsigned overflow. And an unsigned overflow means that the result is not valid as an unsigned chart. Now you're going to run into these kinds of circumstances if you get digitizing values. For instance, if FF is 10 volts, and you had a very small voltage, you're going to end up with a very small voltage, almost 0. So adding 10 plus a little bit gives you a small voltage, doesn't make sense. So in code, when you're digitizing something, you say, if my A to D value here, when I add it, ends up being smaller, I can make this my maximum, which in this case would be 10 volts. So there is ways to get around it, but we do have something called unsigned overflows for unsigned char. So every time you see a C equals 1, and that's what you're going to see in here, whether you do a carry or borrow, that means you have an unsigned overflow. Now, what we saw before is we have a calculation. This is our unsigned chart. This is our signed chart. And what we saw before was we had a calculation FF plus 1. And what we saw was this was a carry and a 0, 0 because it could not be represented properly in our unsigned line. However, FF plus 1 is not a problem here because FF is -1 plus 1 is 0 makes perfect sense. So for our signed chart, the carry is not how we determine whether or not we have a signed overflow. So let's take a look at how that works. For instance, if I do this math, 7F plus 1. If you look at that, that's 80 plus no carry. Let's look at this calculation up here. 7F plus 1 is 80. Makes perfect sense, and no carry here says I did not go past the bounds of my unsigned numbers. However, let's take a look here at our sign chart. Sign chart 7F is 127. I have $127. Somebody gives me another dollar, and I'm $128 in the hole. This is a problem. How's that? Well, this is a positive plus a positive, and I got a negative result, which doesn't make any sense at all. Okay? So, what we're going to say is, what about the other end? If I say 80 plus 7F, or sorry, FF, my mistake, 80 plus FF, if we do that calculation, we see 7F plus a carry, which means I'm as far in debt as I can go. I go another dollar in debt, and then I have all the money in the world. And this doesn't make sense because this is a negative plus a negative, and I didn't get a negative, I got a positive result. This is called a signed overflow. But notice also that since the carry set, the answer 7F by doing this calculation is not valid here, but it's definitely not valid here either. Now, when we take a look at our signed number line, we have something called the signed overflow. Now, the C bit is called the unsigned overflow. Here we have something called V. V equals 1 indicates that we have a signed overflow. And the concept of a signed overflow is quite simple. If you add a positive to a positive and you go past the positive end, that is a signed overflow. If you add a negative to a negative and go past the negative end, then this is a signed overflow because the number will not fit in our signed line. So how do we write this up? Basically, for a signed overflow, if you add two numbers of the same sign, and get a result of opposite sign. So this is what a signed overflow is. Now, if we want to diagram that a little bit, so only if you add two numbers of the same sign. So if you've got this written down somewhere, here's the concept. You can get a signed overflow if you add a positive plus a positive and get a negative. V is 1. If you add a negative plus a negative and get a positive, V is 1. However, if you add a positive plus a negative or a negative plus a positive, V is 0. And why is that? Because if you add a positive and you can go over this end, but if you add a positive to a negative, you're in the middle somewhere. Okay? And the other thing is, so these are V equals 1. If you add two positives, get a negative, add two negatives, get a positive. Also, if you happen to do the normal stuff and say I've added a positive plus a positive and I got a positive, V is 0. If I add a negative and get a negative, V is 0. Because that's what you expect. When you get something you don't expect, V is 1, which is our signed overflow. Now, there's one thing that you should be aware of. So let's take a look at a quick calculation for this. Let's take a look at something like 8a plus 6e. Just looking at these, you can say to yourself, well, 8, is that positive or negative? Well, what is the most significant bit of 8? Is a 1. That means as a sign number, that's negative. 6, the most significant bit, 0, 1, 1, 0, that's a positive. So if you add negative plus a positive, V is 0. So you can tell right away that only adding numbers of the same sign. However, when you take a look at subtraction, it's a little funny. So if I say 5 subtract 3, that's the same thing as 5 subtract positive 3 or 5 plus negative 3. And if you understand this concept here, we can convert a subtraction into a 2's complement addition. Because what does a 2's complement do? The 2's complement gives you the negative of this. So negative 3 and 3, that's the 2's complement. So let's take a look and see what that means. So if I do a subtraction, how do I figure out the overflow? Well, let's do a number like this. Let's do 3a minus 9c and see what happens here. So let's do the calculation. If we do that, we have to borrow 1, c is bigger than a, borrow 1 from the 3, make it a 2, that's a 1a, which is 26 minus 12, which is 14, which is e. We borrow 1 from the carry, that's 18 minus 9 is 9. And so we've got a calculation here. So if we look at it, we've got a result. But what we want to do is figure out, is the overflow set by this? The signed overflow. Well, if you look at 3a, that's a positive, and you're subtracting a negative. But as we just saw, if you want to convert a subtraction into an addition, you have to add the opposite sign. So if this is a positive subtract a negative, that's the same thing as a positive plus a positive. And in this case, we've got a negative, and therefore B is 1 for this guy. So when you're doing subtractions, you have to rethink. You don't have to do the calculation, but you have to think, what would this be as a 2's complement addition? If this is the same as a positive plus a positive and got a negative, you got V equals 1. If, however, you had some other number, let's try another example. If I have 3a minus 6f, let's take a look without even doing the calculations. This is a positive, subtract a positive, right? Which is the same thing as a positive plus the opposite of this, a negative. Adding numbers of opposite sign, v is 0. So it's going to take a little while to get your head around this. And so what we're going to take a look at is n, z, v, and c in total. Let's take a look at that next. Okay, let's do this addition. So this would be like a 5-mark kind of thing, 1 mark for the answer, 1 mark for n, z, v, and c. So let's see how this works. So 13, this is 13 plus 11 is 24, which is 16 plus 8. 10 plus 1 is 11, plus 12 is 23, so I believe that's 78. So when we take a look, you're asking yourself, well, let's just move this n, z, v, c down just a little bit here. So how do we know what is n, what is z, what is v, what is c? Well, n is the most significant bit of our 8-bit result. Our 8-bit result is 0, 1, 1, 1, 1, 0, 0, 0. So this is our n bit. So if we thought of this as a signed number, this number would not be negative. Not negative. Now we also see here we have a carry, or in our case it is carry because we're adding. And let's take a look at what kind of numbers we have here. This is a negative plus a negative, and strangely enough, it gave us a positive, so our b bit would indeed be 1. Now, here's the thing, for z, so this is the MSB of a result, this is the carry, which in our case says unsigned overflow, signed overflow. This result is not valid in either number system. So, what is the z bit? Well, first of all, this says non-negative, yes, signed overflow, yes, unsigned overflow. Is this number 78? Is it 0, 0? And our answer is not 0. So only for 0. Now 0 is probably the most important number there is, because you do not launch missiles at 5, 4, 3, 2, or 1. You launch missiles at 0. So 0 as an 8-bit result is a very important result indeed. Now let's see if we can cook up a number that will add up to 0. So here's what we can do. We can do 0, 0 minus AB, for instance. Remember seeing this? Well, one of the things you're going to learn is that if you take FF and subtract the number, that's called its ones complement. Because if you look at the original binary we did, if you invert numbers, a 1 is a 0 is a 1, you add those two numbers together, you're always going to get FF. So FF minus a number in hex is always the ones complement. How do you get the twos complement? You add 1, and that becomes a 2's complement, or the negative of this value. Well, here's the deal. Adding and subtracting can be done equal operations. So FF minus a number plus 1 can be rewritten as FF plus 1 minus the number. Now, if you do this, what does that mean? FF plus 1 is really 0. Subtract the number. So what we're going to get here is the 2's complement of AB, which is a negative of AB. So let's take a look at that. And we're learning a little bit as we go. So again, the lazy Joe over here and hardworking Bob. So Bob's going to take out the loan. He's got 16. He gives 1 of that to lazy Joe here. So he's got 16 minus 11 is 5. So we've got 55. Now if you add these two, you will get 0. So here's the thing. If I take AB plus 55, I just cooked it up, AB plus 55, let's see our NZ, whoops, let's move this down, NZ, V, and C for this guy. Okay, so 11 plus 5 is 16, which is 1, 0, 1, 0, and what do we have? The most significant bit of 0 is a 0, which is not negative. What about our carry? We had a carry. This is a negative plus a positive, so we do not have a sign overflow. And this, yay, this is a 0. This is the only one. It's like Tigger is the only one. So only when you hit 0 is this 1 saying, yes, I got 0, I'm special. So you should be able to figure out the NZBCs for all of these, and as before, if you have to convert the binary to hex to do it and convert back, then the most significant bit is the N bit. If it's 0, it's a 1. Otherwise, for all other 256 all other 255 numbers, it's not 0. Only 0 is 0. Not a signed overflow, and yes, a unsigned overflow. So you should be able to do the NZBC stuff from here. Okay, let's take a look at unsigned integer and signed integer. Now, on any term test or anything, I'm never going to ask you to do this by hand because it's a little more tedious. But we're going to take a look at the differences between these. Now notice, in this case, as we saw before, n is 0, positive. N is 1, positive. Over here, n is 1, negative. N is 0, positive. So what we have here is instead of having 256 different numbers, we have 65,536, which is 0 through 65,535. Now what we should be able to do is convert some numbers over here, 53,000 something over here, convert that to hex and see that we can indeed do that and just show that it is possible. Now in DGS you're going to convert decimal to binary by divide by 2, divide by 2, divide by 2, divide by 2, or if you want the shortcut, divide by 16 and convert back. So let's take a look. We're going to come back to this in a second, but in the book it says, or in the lab rather, it says to convert 50,000 something. So I'm going to actually show you how to convert 50,000 from decimals over here to hex, and you should be able to do a similar calculation for the one that's in the actual lab. So here's what we do. We divide by 16. So 16 goes into this 3 times, which is 48. That gives us a remainder of 2. Once, 16, 4, bring down to 0. That goes 2, which is 32, which is 8, bring down to 0. 5, and that's 80 with 0 remainder. So that's what we've got now. Now what we're expecting out of this is a 4-digit hex number. And this digit here will be the rightmost digit, or 0. So we've already figured out 1. And once we figure that out, what we have left is 3,125. So what we're going to do is now divide 16 into 3125. And the next remainder is going to go here. So let's do that. That's 1. And this is going to give what? 15. Bring down to 2, which is a 9, which is 144. That's 8. Bring down to 5. That goes 5 times. That's 80 with 5 remainder. There's our 5 sitting here. Let's redraw that. That's a 5. Now, we've got 2 of our 4 digits. To finish this off, all we have to do is divide 16 into 195. Let's do that. 16 goes into 195 once. 3, bring down to 5, 2, 32, and this is 3. So that becomes C, 3, and you've done it. Okay? So what we've got here is, even though it's a little tedious, you can convert a number like 50,000, which we started off with, into the equivalent base 16. So we can do that. Now, it also says in the book, or sorry, it also says in the lab that we want to convert a negative value. Now, I'm going to convert the number minus 20,000. I'm not going to pick exactly the one that's in there. Now, if you remember how this worked before, our 8-bit stuff was shifted by 2 to the 8, or 256. So we subtracted from 256. In this case, we're shifting 2 to the 16, which is 65,536. And so all we're going to do is do the subtraction. This is 6, 3, 5, 5, 4. And this is a number that we're going to continually divide by 16 to come up with the right answer. Because this 20,000 is offset by the other 20,000 by 65,536. So that's why we do this here. So we're going to start with that. So it's 45535. 16 goes into this. 2, 32. 13, bring down to 5. 7, 8. 8, 6 is 48. 12. So that's 7, bring down to 3. That's 4, which is 64. 9, bring down to 6. And what do we have? That's going 6, 96, which is going to give us a rightmost digit of 0. Then we're going to divide 16 goes into this. 16 goes into this. Once. 2. That's 12, bring down to 4. 8. Oops, 7. That's 2. That's 1, bring down to 6. And that's, let's see, that's again 7. So what we have here is that happens to be an E. Then we divide 16 into 177. And we're finished. That goes once. Bring down to 7. That goes once. Which is B1. Now, if you think about it, to make sure this is a negative answer, the most significant bit of this answer should indeed be a 1. And B starts 1, 0, 1, 1. So we're pretty sure that this is the right answer. So these are steps you're going to have to do the last question in lab number 1.